Okay, so on this page, 5.4, internal energy, sum of random distribution of kinetic and potential energies of molecules in a system. So this one you have to memorize it. They ask a lot. The random distribution is the keyword. Okay, so it means that internal energy has two parts. It is the sum of the kinetic energy and the potential energy. How fast it moves and how far they are separated. So that is the potential energy. Potential energy is affected by how far they are separated. So where that time I discussed with you before, where I said if they are having a greater distance, I mean the particles have greater distance from each other, then their potential energy is higher. Potential energy is higher. So I write down at the side first. Kinetic energy, if it's fast, then kinetic energy is high. Very easy. Potential energy, if they are far apart, then potential energy is high. So if you sum up kinetic energy and potential energy, then we call it internal energy. So why they have to put random distribution? Because different molecules or different particles, they have different kinetic energy. So it distributes randomly. Okay? And potential energy also. So they have different potential energy as well. Different particles have different potential energies. So internal energy is the total of PE plus the total of KE. You add up the energies for all the molecules, and then that is the internal energy. So next point, a rise in temperature of a body is an increase in its internal energy. Okay, so should be common sense here. First, if you increase the temperature, the particle move fast, then they are having greater kinetic energy. If you increase the temperature, the particles move further away from each other because they are having more kinetic energy. So they are further apart, then the potential energy is increasing. So if these two increase, and you look at this equation, if this one increase, then internal energy should be more. Further apart, and more kinetic energy. Okay, so of course maybe I have to say this one increase a lot lah. This one maybe not so obvious. Depends on how much you heat it up, So if you heat it up until it becomes gas, right? So this one will increase a lot. But if they are still solid, right, you should not expect this to increase a lot. Solid have no space to very limited space for them to expand also. So limited very little increase in potential energy if that is the heating up of solid. Okay, no matter how, we move on. First law of thermodynamics. So the law is here. The increase in internal energy. So this is called the delta U. Of a system. So the system is like the gas or the liquid or the solid. So that's the system. Is equal to the sum of heat supplied to the system and the work done on the system. So there are two parts. The increase in internal energy is equal to Q, The Q here is the heat supplied to the system. Heat supplied to the system is the one that we count before, which is from the previous page 2 just now, where we use the just now we use E lah. Now they use Q already in a sudden, okay, and they don't standardize the symbol also. In a sudden they use like here, they use Q, then in a sudden they change the capital Q. So let's say I standardize it myself lah. Okay, so this is the E, because just now we use E, so now I use E again. Okay, I use E. So the E there, heat supplied to the system, you can get it by using MC delta theta, ML fusion, ML vaporizations. So you can use this to get the E, the heat supplied to the system. And for the W, which is work done on the system, so you can think of work done. I can write here. This is the E, the W. W equal to P times delta V. P times delta V. And I have a suggestions. So you can fix it this way. It will be convenient. Initial volume minus final volume. Initial volume minus final volume. So how good is this? Let's say imagine if you heat and let's say the volume increase. Volume increase. So in that case, initial volume should be lower than final volume. Try to imagine that. Because of the increase of volume, final should be greater. So we should expect delta V to be negative. So W equal to P delta V, then this should be negative. This should be negative. So you should expect negative for work done. So this is known as work done by system. The system means the solid, liquid, or gas. So the expansion of solid, liquid, or gas here will make the work done to be negative, and we call it work done by system. So which means what? The work is done by the solid, liquid, gas to push against the atmosphere. It's work done by them to push against the atmosphere, the surrounding. Okay, so if it is the other way around, let's say for example you cool down, the volume decrease. So now you have to imagine again. Volume decrease. That means final should be small. Initial should be big. Big minus small should end up with delta V that is positive. So our delta V is positive. So W equal to P delta V. So your W should be positive now. If your W is positive, so we call it work done to system. Work done to system. How to understand work done to system? The system is solid, liquid, or gas that I said. Work done to system is like the surrounding or the atmosphere is pressing the the solid liquid gas, that means pressing your system and make it decrease in volume. Make it decrease in volume. So that is where W is positive. This one easy. For E, for E just now, I forgot to mention when is it positive, when is it negative. So this is easy because we learned long time ago. E is positive when it is endothermic. Endothermic or heating lah. Okay, heating. And E is negative when it is exothermic, or in other words, cooling. Okay, that is easy. So altogether we have two formula. The first formula is internal energy equal to total potential energy plus total kinetic energy. You can modify this formula a little bit. This is the formula. You can modify it to change in internal energy is equal to change in potential energy plus change in kinetic energy. Can also. You can modify it in this way. Okay? Then if I modify it in this way, then we can easily relate this formula to this formula. Change in internal energy is equal to the heat supplied to the system plus the work done on the system. Okay, you can see that they use work done on the system. They are using work done by system. This one, they are using work done to system, work done on the system. They are using positive. Work done to the system, or work done on the system. Work done on the system. They are using the positive situation because you see our formula, right? W is taking positive sign. W is taking positive sign. So that means it is W is positive, work done on the system or work done to the system. E is positive sign also because the front part is positive. Okay, so positive means endothermic or heating. So heat supplied to the system. So heat supplied to the solid, liquid, and gas. Okay, so now let's practice. Write down the symbol positive for increase, the symbol negative for decrease, and the symbol 0 for no change. Okay, so you may use or you may consider the formula on top, this one, or you may also consider this formula, which is the first law of thermodynamics. So you have two choices of formula to be considered. Okay, so let's see the question. The compression of an ideal gas at constant temperature. Okay, so Q and W. This Q I change to E lah. Okay, since I set already, I set the E as the heat energy as E, so I will remain it E and W. Okay, so first let's think about compression. Compression will make the volume decrease. The volume of gas decrease. Volume of gas decrease. So you should expect, as you can see here, I try to point here. Okay, here, volume decrease. Compression volume decrease, W is positive. Okay, I write down first. Volume decrease, W is positive. Okay, positive. Now we talk about the E now, the heat energy. So the heat energy, is it positive or negative or what? So it depends on whether it is endothermic or exothermic. Okay, so to decide on these, we have to think. We have to think like this. When you compress the gas, it is a situations where the gas molecules or the gas particles are coming closer together. So it is very similar to the condensation of gas. Very similar. Okay, this is a bit hard. I write down the explanation here. Compression causes gas molecules to stay closer. And this process is very similar to condensation. Okay, let's think about condensation. You have to think about whether condensation is endothermic or exothermic. Okay, so to think about this, right? Boiling, right? Boiling, you need to supply heat. You need to heat up the water, then it boils. So it's endothermic. So condensation is the other way around. So it's exothermic. So this should be exothermic. 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 Okay. So at the end, our E should be negative. Okay. So the other thing is the U. The U or the delta U here should increase or should decrease. Okay, so we need to think about this. How we think about it is it depends also lah, the 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 increase or the decrease of U. It depends on whether the work done is bigger than the E or the E is bigger than the W. So it depends on that also. So over here we have to take it in this way. We have to take it in this way. I write down for you. Increase in work done is balanced by the gas heating. So net remains 0. Okay, so net remains 0, and internal energy unchanged. Okay, so this should be 0 then. So they are like balance each other. Okay, so This is the situation. Okay, now let's look at part 2 then. Part 2, the heating of a solid with no expansion. No expansion. So let's focus on no expansion. So no expansion, very obvious. Change of volume is 0. And when there is no change in volume, so W is equal to 0. The work done is 0. So this is 0. This is obvious enough. And the second important keyword is the heating of a solid. So this is endothermic, positive. So based on first law of thermodynamics, so we have to say that when the W is 0, as you can see the equation, 0, this is positive. For sure, delta U will be positive. Okay, so positive for this. Now, part 3, the melting of ice at 0 degrees Celsius to give water at 0 degrees Celsius. Ice is less dense than water. Okay, so to think about this, first, let's see the change of volume first. Ice is less dense than water, so meaning that the ice is less dense. The ice is like expanding a little bit. That's why it's less dense, expanding a little bit. So then it floats. But the thing is, the change of volume is too small actually. The change is too small. Okay, so let's say I bring it down here. Okay, maybe I use different color. Okay, blue color. Okay, change is too small. Okay, maybe I hold this first because change is too small, or is it too small? We consider 0 or still consider small positive value. Expand. Yeah. So should be 0 or should be small positive? I hold it first. Let's see other first. Okay, the melting. So melting, obviously, melting is endothermic. Endothermic. You need to supply heat to make it melt. So endothermic is obvious enough for melting. So this is positive. Now, no matter uh, no matter the work done is 0 or small positive value, where we assume they expand a little bit, at the end for sure, this is increasing or increase too little, we ignore. This for sure increase. Delta U for sure increase. Okay, so this one for sure it increases. Now in these situations, how we think about it? Okay, so my uh, my suggestion is like both will be just fine, so based on the mark scheme, because this is a past year question, they put 0. So meaning that they okay they expect the change in V is too small and ignore. Okay, so let's move on. Some water in a saucepan is boiling. Explain why external work is done by the boiling water. External work done. So external work is done by the boiling water. So which means work done by system lah. Work done by system, which is this situation. Work done by boiling water. W is negative. Volume increase. Okay, you boil the water, right? So the system here include the boiling water as well as the steam. So the boiling water and the steam, they are very hot. They are pressing against the atmosphere. Okay, so now we have to explain it. Volume increase is the keyword. So volume increases due to evaporation or boiling. The volume of the system increases. Okay, so the water turn into gas. Okay, so work is done by the boiling gas, boiling water against the atmosphere. Okay, number 2. There is a change in the internal energy as water changes to steam. Water changes to steam. So this is very similar to the first one. Water changes to steam. Okay, so water changes to steam. Internal energy. So you have two options here. Either you stick to first law of thermodynamics, or you stick to this one. It's up to you. Okay, so there are two formula to be considered. The potential energy and kinetic energy, or this one, E plus W, first law of thermodynamics. So both will be fine. Then you have to say at the end this delta U increase. Okay, so for the answer that I have here, they are using this. Both will be fine, like what I said. They are using this. Okay, now let's see. Water changes to steam. Okay, I write down first. Considering delta U equal to delta PE plus delta KE. Okay. If you want to consider first law of thermodynamics, the explanation works also. Okay. So what I say is the kinetic energy the kinetic energy of molecules is constant as no temperature change. You know, boiling happen at the same temperature. Huh? Okay, so the potential energy increases because of increase in separations of molecules based on delta U equal to delta PE plus delta KE. Internal energy increases. So this is where we consider it based on the first formula. If you want to consider it based on the first law of thermodynamics, can also actually. So first you say, it is endothermic. Endothermic is boiling, right? Water change to steam is boiling. Endothermic, positive. Okay, so change in volume. Volume change in volume increase. Volume increase, same like this one. Volume increase due to evaporation or boiling. So work is done by the boiling. Okay, so that is where W change in volume is positive. So if change in volume, okay, volume increase, then W is negative. W is negative. So this is positive, this is negative, this one not sure. Okay, so seems like having problem if you use first law of thermodynamics. Because it's endothermic, this is positive. Work done is negative. Work done is negative. As you know, volume increase, right? So work done is negative. Then this is positive or negative? Not sure. So there is a problem. If you look at first law of thermodynamics, you will feel like it has problem. Not sure. So of course, if you are not sure, then you look at this. This is the second alternative. Second alternative. Okay, so this one very confirm. Potential energy increase for sure. Kinetic energy no change because no change in temperature. So this positive, this zero, delta U must be positive. Must be positive. Okay, so we look at B then. By reference to the first law and your answer in A, show that thermal energy must be supplied to the water during the boiling process. That means you have to show E must be positive. E must be positive. So first law, delta U equal to E plus W. From part 2, there is an increase in internal energy. Okay, so meaning that from A part 2 we already know this is positive. Okay, then from part 1 work is done by the boiling water and W is negative. So E equal to delta U minus W. You rearrange it. So you know this is positive. You know this is negative. So at the end, there is another negative to balance back and it become positive. So E must be positive. It's because right hand side is positive plus something. So E must be positive. So E must be positive. Okay, so we settle for this.